Hello, my name is Eleni Margariti, and I will present our paper evaluating ActuAir, building occupants' experiences of a shape-changing air quality display. With workplace buildings becoming increasingly sensor-rich and amidst climate change and global pandemic, there is novel opportunity for utilizing climatic data within buildings for awareness and well-being purposes. Interaction design research, however, including on large shared displays, rarely addresses building occupants' experiences of air quality. Responding to these research gaps, we made and evaluated ActuAir, a large shape and color changing display responding to air quality data. 3 prototype-led studies were conducted with 21 occupants of a smart office building over June, July, and August 2022, evaluating their experiences with the display. Contributing to human building interaction research, this paper provides with design implications for shape and color changing displays for communicating air quality data, and provides direction for future research on shape-changing architecture for climate awareness in smart buildings. Other physicalizations for climate and breathing awareness have been explored as wearable, small-scale, and tangible interventions, but rarely at the level and scale of an architectural intervention, highlighting research gaps in the contribution of our current work. One of the limited examples of large-scale data physicalization for air quality is shutters. Shutters is an example of physicalizing air quality data in the workplace, engaging with a shape change at the architectural scale to communicate data. More contemporary approaches are the atmospheric interfaces agenda. We particularly engage with soft robotics and actuating materials research to develop ActuAir. Soft robotics is an emerging agenda with human-computer interaction research that engages with robotic systems and metamaterials that imitate living tissues, heavily influenced by biomimicry and biophilia, extended to the design research on shape and color changing displays. Examples of soft robotic displays include works using smart memory alloy actuators, pneumatic interfaces, and inflatable artifacts. Soft robotics often address modularity. Modular displays provide enhanced opportunities for user customizability, addressing aspects of physical scale and the marginality of feedback in the buildings and creating opportunities for swarm robotic behaviors. ActuAir prototype consists of 8 custom silicon rubber pouches with embedded NeoPixel LED stripes attached on 8 prefabricated modules, forming a customizable modular room divider. The silicon rubber pouches inflate and deflate based on different air quality data levels. In the default setup, the amount of inflation is proportional to the selected data stream. The inflation effect is enhanced by the embedded LEDs, which obtain a green to red color range proportional to preset air quality levels. Each module operates with a wireless Arduino connected to a local web server. Being modular, the display is highly configurable by the building occupants. Feedback produced by each module is also highly customizable to assist with the research purpose of the display. The web server provides a control panel, which enables the researchers to choose different data streams and building locations, choose which modules display which data, and manipulate feedback, manually control inflation and deflation, and LED animations of a given module. Biomimicry is conceptually at the core of the design of intervention. Design was inspired by natural algorithms and the metaphor of breathing, translated to inflation and deflation. Three successive studies took place between June and August 2022 to evaluate ActuAir display. The studies overlapped with regards to what aspects they explored, but they also informed each other based on key findings. Study 1, ActuAir Design Criteria Evaluation Workshops, was a series of design criteria workshops led by the prototype's installation in a meeting room, exploring the feedback perception of 9 experts and simultaneously occupants of the building in a controlled setup. The aim of Study 1 was to unpack the pros and cons of the display's materialization and functionality and define the conditions for one or more deployments in the building. Study 2, Biomimicry Feedback Creation Workshop, was a co-creation workshop facilitated by the prototype's installation in a meeting room, exploring feedback perception and interpretation and controlled setup. 5 participants were shown 5 video-recorded biomimicry feedback configurations of the prototype, while also experiencing the prototype installed in place. The participants were asked questions around what data was represented and how they interpreted different feedback scenarios. Finally, the participants were asked to vote for which one appealed to them the most and co-design their own modular configurations using paper templates. Study 3 was a 2-week case study of deployment in the building. The deployment setup was driven by findings of both Study 1 and 2. Study 3 aim was to map aspects of shape and color changing feedback experience in situ. Workshops and interviews during Study 3 were video recorded and transcribed. Data from all studies were qualitatively analyzed and produced key themes and design implications. These are briefly presented here, but please see our paper for further details. In terms of theme A, physical and spatial aspects of feedback perception, design implication 1, module's positionality key for shape change readability. Results from Study 1 and 3 highlighted differences in participants' awareness and perception of shape change depending on the display's physical positioning. Design implication 2, utilizing outlines and shadows to enhance shape change. To address shape change readability issues, participants suggested the use of spotlights or sidelights to enhance the outline of the inflatables and utilize their shadows as part of the experience. Design implication 3, light diffusion pulse, key for inflation perception. Participants in Study 1 and 3 further acknowledged that the embedded LEDs play a key role in enhancing shape change awareness. They found the light diffusing effect intriguing. The coordination of inflation and LED animations was extensively discussed by participants in Study 1 with a view to better support inflation awareness and feedback perception. Participants suggested effects such as light pulsating when inflation was reached its maximum, or that the pouches can stay semi-inflated to diffuse light better. Design implication 4, light as material. In Study 3, participants' observations highlighted the experience of the color change and the aesthetic aspects of inflation and materiality. With inflation changing light distribution, and even the color of light changes because of inflation. The light becomes brighter than when it deflates. Design implication 5, circularity in spatial data associations. Results in Studies 2 and 3 illustrated how the modularity of the display inspired thoughts of specialized data representations. Participants thought it represented an area or areas in the building. Theme B, biomimicry, materiality and embodiment. Design implication 6, form and material key for environmental associations. Participants in all studies intuitively related the display to climatic data based on shape and design factors, such as color and material properties. Illustrated in quotes such as, "It is green, has leaf-like shapes. It is nice how material is making light diffuse, resembling something from the ocean," or gluey texture. Design application 7, light and inflation coordination enhances climatic associations. Participants Study 1, inspired by the prototype's physical properties, saw the coordination of inflation and LEDs and the adoption of biomimetic metaphors as a way to better support feedback awareness and intuitive interpretation of the display, and potentially link it better to CO2 data representations. Some participants suggested abandoning use of the traffic light system to represent CO2 levels in favor of using 2-color and 1-color representations, gradual transitions between colors, and LED animations to draw attention, such as light blinking or pulsating at critical moments. Design application 8, color drives feedback interpretation. Across studies, LED color was seen as a dominant mechanism to communicate both absolute and relative information, as well as the rhythm of change of data streams. Theme C, feedback repetition, rhythmicity and momentum. Design implication 9, rhythm of feedback, important for awareness. The appropriate coordination of LEDs and inflation was framed both in the context of creating momentum, when significant change in air quality levels takes place, as well as in the context of creating a sense of pacing and rhythm in the display's operation. Design application 10, noise as feedback at key moments. Participants in Study 1 and 2 suggested that noise can be an essential interesting feedback parameter to be used with caution. Design application 11, speed of light animation linked to urgency. Study 2 illustrates these variables, such as speed of control transition, the color range of LED animations or repetition, are key to feedback interpretation. A gradual, non-repeating green to red transition at a speed of 30 seconds created a clear perception of slow deterioration, whereas the same animation at 5 seconds speed created a sense of urgency. Design application 12, feedback expectation impacts attention. It became apparent that observations from a control setup do not necessarily apply for in the wild deployments. For instance, traffic light color range and non-gradual color range were seen as limiting in Study 1, On the contrary, the idea of a traffic light system was treated positively in studies 2 and 3, as it was easy to interpret and predict. Theme D, data use, interactivity, and configurability. Design application 13, spatial context influences data use. The display's location in the workplace created different expectations in terms of data used and feedback configurations. Design application 14, feedback tailoring based on occupancy and proximity data. Beyond air quality and climate data, there were some ideas around integrating different data sources, including for human activity. This would strengthen human data interactions. It was also suggested that motion and occupancy sensors could be used to also control the overall powering of the intervention, voicing concerns over energy use. Design application 15, extending modularity and plug and play. Enhancing the existing customizability of the display and designing tools to allow further configuration and manipulation by building occupants. Findings from both control studies, such as 1 and 2, and in the wild deployment, study 3, are discussed below as design implications and opportunities for future research. We have put together a table summarizing our design implications as derived from the findings and how these are translated to design recommendations for different types of displays, including modular, shape-changing, and broadly physical displays. Please see our paper for further information. Finally, we conclude with areas of future work for the design space of modular soft robotics for large physical displays for climate awareness. These include 1. Further research on actuating materials in office buildings to support embodied climate awareness through biomimetic, haptic, and tangible feedback. For instance, soft robotic skin textures that imitate bodily responses to climate. 2. Further research in biomimetic and biophilic design for physical displays, including biomaterials for capturing CO2, with a focus on nature-derived light and color feedback. 3. Self-powered or low-energy physical climatic displays, focus on biomaterials and mechanisms to drive energy saving. 4. Feedback to support awareness on collective and individual climate behavior, linking the display's operation with data on human activity in the building, including open and windows, occupancy levels, etc., and the individual and collective contribution to CO2. 5. Research on further utilizing noise in pneumatic systems as part of a feedback strategy. 6. Further research on swarm behavior and modular feedback systems to support further specialized understanding of climatic data. And 7. Interfaces for user control of modular displays, including modular robotic interfaces that incorporate different types of feedback customization and data source selection through mobile and tangible interaction. Summarizing, through mapping building occupants' experiences of a modular soft robotic shape and color changing display of climatic data in a smart workplace building, we have brought to the fore several design implications relevant to the application of soft robotics in that context, also extended to the design and deployment of modular, shape-changing, and broadly physical displays. We contribute to human building interaction research through opening the design space of modular soft robotics for large physical displays for climate awareness, presenting existing opportunities and challenges for the deployment of such interventions in smart office buildings. Thank you.